In this lesson, we're going to have a look at some examples of the way the index laws can be used to simplify expressions. Now, in this particular case, the best way to start is by expanding out the numbers. So we've got 3 times y to the half times 2 times y to the half. You will find that you won't need to expand these once you've done these a few times, but just to start, it's a good way so you can see how things work. Multiply the numbers together. 3 times 2 is 6. And then using our index laws, we find the numbers with the same bases, in this case y, and because we're timesing them, we add. So it's a half plus a half. We get 6 times y to the 1, and this can simplify down to 6y. We have a division here, so let's write it as a division. 10n to the power of a third divided by 5n to the third. Now, what we can do here is to cancel out by dividing the highest common factor of 10 and 5, that's 5. So 5 into 5 goes 1, 5 into 10 goes 2. And we're ending up with 2 at the top and a 1 at the bottom, so we can leave that down there for the moment. And then we apply our index rules to the n. So that's 1/3. And because we're dividing by n to the 1/3, we can subtract the indices. So we're left with 2 times n. Now it's a third minus a third, which gives us 0, all over 1, which we don't need to write in now. And once again, remember that the power of 0 only applies to the n. So I'll just expand it out, and this is what it means. So we can finish it by applying the 0 rule. N to the power of 0 is 1, so our answer is 2. In this example, we're multiplying. There are the same bases, so we add our index numbers. So it's m to the minus 6 plus 2. As you can see, we get minus 6 and 2 gives us a minus 4. What we'll do finally then is to write it out with a positive index, m to 4. Now this is exactly the same as this one. In this one we've got a division, so we know that we're going to be subtracting indexes. So we'll write it as a division first of all. We know that we've got the same bases, so we're subtracting the indexes. That's minus 7. As you can see here, when you've got two minuses together, a minus and a minus number, that will give us a plus. So we end up with q to the minus 2 plus 7. And finishing this off, minus 2 plus 7 gives us a 5, a positive 5. Minus 2 plus 7 is 5, and there's our solution. In this last example on this page, we've got a base to a power, and that has a power outside. So we times our 5 with that. I'll write a little equal sign there. So our final answer is minus 3 times 5, which is minus 15. And can be left like that if you need a negative index, but remember it can be written like this if you want to have a positive index. This time we won't expand it out, we'll just do it as if it was expanded out. So this is 5 times m to the minus 3. Now remember, the minus 3 links to the m, not to the 5. So in fact, the answer here is 5 times 6, which is 30, and it's m to the minus 3 plus 7. So that gives us our 30. M minus 3 plus 7 is a 4, positive 4, minus 3 plus 7, and there's our solution. I'll remind you again, the difference between this and it's not equal to this. Here the minus 3 relates to the 5 and the m, here just to the m. In this division we have 4y to the 7 divided by 5y to the minus 2. Now you'll notice that there is no other high common factor other than 1 for these two. So in fact 4/5 just remains 4/5. But we can do something with these ones. They're the same bases and it's a division. So remember we subtract the indices. So it's minus 2. And once again we remember that these two minuses together give us a positive. So our final answer is 4y to the 7 plus 2, which is a 9, and the 5 remains in the denominator. Now here's a question that relates back to this fact, and that is that the 3 links with the 5 and the y. So what we're going to do is we will expand this out, put our bracket around it, and there's our power of 3. And we need to take this and multiply it with the power here, which is a 1. Remember, when there's no power, or you can't see a power, it's actually a 1. So we're going to times those together, and we're going to times those together. We do this in this way. Here's our 5 to the 1, and we times this with a 3, times by, there's our y, and there's our minus 2, and we times this by 3 as well. Let's finish this off now. We've got 5 to the 3 times y to the minus 6. We can multiply this out. 5 cubed is 125. And our y to the 6, now that's a minus 6, so we can actually move that underneath like this. It's better to have positive indices in an answer. So it's 125 over y to the 6. Remember that this is equivalent, this part here is equivalent to 1 over y to the 6, and that's why it appears down here in the denominator. We've got 4 questions here that we've got to work out whether they are actually true or false. So the best thing to do is to look at the left hand side, see what that works out to be, and if it's equal to the right hand side, then we know it's true. So in this case we've got the left hand side being m to the 3 divided by m to the 5. So we can say that would be m to the 3 minus 5, which is equal to m to the minus 2. So the left hand side is not equal to the right hand side in this case, because the right hand side is m squared. So the answer would be false. Here we've got the left hand side equaling 3 times y to the 0. Remember, the 0 relates to the y because there's no bracket. It doesn't relate to the 3. This would leave us with 3 times 1 if we apply our rule, which is 3. So once again, the left hand side does not equal the right hand side, being 1, and so it's false. Let's try this one here, C. We've got a left hand side being equal to 6 k to the 4 divided by 2 k to the 4. We'll write this as a fraction, 6 k to the 4 divided by 2 k to the 4. We can cancel these out and we're left with a 3, and we can then apply our rules. That's 4 take away 4 in the index. That leaves us with 3 times k to the 0, which is equal to 3. And if we check it here, we can see that the left-hand side does equal the right-hand side. So here the answer, or the expression up here, is true. Our final one, our left-hand side, equals 2p to the minus 3. Expanding this, we can see that the minus 3 only relates to the p and is the same as 2 over p to the 3. And that's exactly what they were testing, to see whether you could see that the minus 3 only related to the p and not to the 2. See, they've put the 2 underneath here. So in fact, the left-hand side does not equal the right-hand side. So this statement up here, I'll put a cross through it, is false. Finally, we'll have a look at comparing two sides, the left-hand side and the right-hand side, to test for equality by substituting in a value. We'll take the left-hand side first of all, and that's equal to a to the minus 2. So now we're going to substitute a equal to 5 into this particular expression. So we get 5 to the minus 2. We could then rewrite this as 1 over 5 squared, which would give us 1 over 25. Let's look at the right-hand side. The right-hand side is equal to minus 2a, which would be minus 2 times a. So we're going to substitute a equal to 5 into this expression, and we get minus 2 times 5. And minus 2 times 5 is minus 10. So you can see the difference in the left-hand side and the right-hand side. And therefore we can say, therefore a to the minus 2 is not equal to minus 2a. And you can see what they were testing here. There's a minus 2 here. Is it the same as having the minus 2 here? Are you timesing by minus 2? Not here, you're not. So you can see that you've got to watch out for some of those little tricks with your index laws.